Okay, so in this video, we are going to talk about transformations of quadratic functions, and we are going to talk about all three forms of quadratic functions because the transformations are the same for all three forms. Okay, basically what a transformation is how a quadratic function is changed from what we call a parent function. Okay, the parent function of a quadratic is y equals x squared. It is specifically where the vertex is at 0, 0, and a, the coefficient that's always in front of the x squared, equals 1. Okay, so take a look. That is what the parent function looks like. The vertex is at 0, 0, and a is 1. Okay, so let's take a look at all three forms just as a reminder. All right, you've got standard form, y equals a, x squared plus bx plus c. Then you got intercept form, which is y equals a times x minus p times x minus q, where p and q are your x-intercepts. And then you've got y equals a times x minus h squared plus k, where hk is your vertex. Okay, so it's just a reminder how all three are written. And all three of them have the same parent function, y equals x squared, where the vertex is 0, 0, and a equals 1. Now, notice that all three forms have the letter A. Okay? All the transformations are based on what number A is and what the vertex of the function is. Okay? A tells us if the function has been stretched, shrunk, or reflected. Stretching and shrinking can also be referred to as a dilation, making something bigger or smaller. And reflected, of course, is just like in a mirror. It flips the graph upside down. Okay, the vertex, which in a parent function is at 0, 0, tells us how far the graph has been moved, left or right, and up or down. Okay, again, there are three transformations that A can take care of, and there's a way to recognize each one. Okay, so if it's going to be a stretch, A has to be a number specifically that is greater than 0. And actually, that's not greater than 0. It's actually supposed to be greater than 1. Sorry about that. Greater than 1. Now, I need you to understand that is the absolute value of the number has to be greater than 1. Okay, because we're going to deal with negatives as well. So for a stretch, A must be a number greater than 1, and you're looking at the absolute value of that number. Okay, for a shrink, A must be a number between 0 and 1. So now you're looking at specifically decimals and fractions that are between 0 and 1. Okay, and here's where it gets interesting why we're looking at the absolute value of those numbers, because if I'm going to reflect the function, flip it upside down, A has to be a negative. Okay, and that means that you can have a reflection and a shrink or a reflection and a stretch. It's possible to get both at once because the reflection makes the A negative, and then the A being either greater than 1 or between 0 and 1 does the stretch or the shrink. So let's take a look and do some examples, one of each form. Okay, so first one, standard form. So the first thing you have to pick out to figure out how much this thing has changed is the vertex. Now remember, in standard form, the vertex is done by the formula x equals negative b divided by 2a. So we substitute a and b into our formula, and that's going to be 4 divided by 2 times 2. So 4 divided by basically 4 is 1. So the x value of my vertex is 1. And then we substitute that back in to see what the y value is. So 2 times 1 squared minus 4 times 1 plus 3. So that's 2 minus 4 is negative 2 plus 3 is 1. Okay, so my vertex is 1, 1. All right, so if you compare that point, right, 0, 0 is the parent point. That's where the vertex is normally starting out. Your new vertex is at 1, 1. That means the graph moved 1 to the right and 1 up. That's where the new vertex is. So that tells us how far left and right, up or down, that it is. Okay, so now we're going to take a look at A, just the A coefficient. Well, the A is 2. That's a positive number, so no reflection. And 2 is greater than 1, which means the graph has been stretched. Okay, so the parent function has been moved 1 to the right, 1 up, and stretched, or basically made taller and narrower. All right, so let's try another. Okay, so this one is in intercept form. And remember, in order to find the vertex from intercept form, we first need the x-intercepts and then find the halfway or the midway point between them. So what are my x-intercepts? Remember that you have to make the y equal 0 and solve each of the parentheses. So my x-intercepts are 1 and negative 5. And then halfway between them, or the midpoint of them, 1 plus negative 5 divided by 2 is negative 2. So that is the x value of my vertex. And then substitute that back in. And what you should get should be negative 27. And it doesn't matter how big it is, you're not actually going to have to graph that. So, but your vertex is negative 2, negative 27. So that means your original parent function, again, which is supposed to be at 0, 0, has been moved 2 to the left and 27 down. All right, and then you take a look at A. A is equal to negative 3. Okay, first off, it has a negative. That means it's been reflected. And the absolute value of negative 3 is 3, which is bigger than 1. So it has also been stretched. So the original parent function that starts at 0, 0 and goes up has been moved 2 to the left, 27 down, been flipped over, so now it's facing this way instead, and has been made taller and skinnier. All right, last one. Now we're in vertex form. Okay, so this one's probably the easiest to do because the vertex is given to us and we don't have to go through the steps to find it. So the vertex on this one is negative 2, negative 3. Don't forget that you have to change the sign of whatever's in the parentheses, change the sign of H. So the vertex is negative 2, negative 3, so that means it's been moved 2 to the left and 3 down. And A is equal to a half. There's no reflection, it's not negative. And 1/2 is between 0 and 1. So it has been shrunk or shrinked, or not shrink, sorry. There is a shrink or it has been shrunk. Okay, and that's it. You're always going to compare the vertex at 0, 0 and A equaling 1 to whatever is different. All right, that's it.